Hello everybody, my name is Carlton Hudson. I go by the name of Network Prodigy. The goal of my YouTube tutorials is to make you a more sound and better network engineer. And the tutorial that I have for you guys today is on BGP route reflectors. So this is the topology that we're going to use. We have routers 1, 2, and 3. 1 and 2 are going to be iBGP peers, so you can tell by the iBGP right here. 2 and 3 are also going to be iBGP peers. 1 and 3 are not going to peer with each other using iBGP. Now each router is going to have a loopback, so router 1 has a loopback, router 2 has a loopback, router 3 has a loopback. The goal is going to be to advertise these loopbacks into BGP, and we want full connectivity between the loopbacks. So that means router 1 should be able to ping router 2's loopback, and he should be able to ping router 3's loopback, for example. Now I'm also running iGRP 100 between the 3 routers. So iGRP is running on this link, and this link. Okay, so for example, if I were to come over to router 1 and do a show IP iGRP neighbors, I'm going to see that I have two neighbors. I have router 2 and router 3 as a neighbor. Now the network has already been pre-configured for BGP. So 1 is pairing with 2, 2 is pairing with 3. If we want to see that configuration, I can do a show run section router BGP. So here's the BGP configuration. We can see we're pairing to routers 1 and 3. We're also advertising our loopback into BGP. If I do a show IP BGP summary, I can see that I have a peer router 1, a peer router 3, and I can tell that the peer is up because I'm receiving a prefix from both of them. If I do a show IP BGP, I can see that I'm learning both of their prefixes. I can see I'm learning it from router 1. I can see I'm learning router 3's loopback as well from router 3. So the goal is we need to have connectivity between the loopbacks. So if I come over to router 2, if I were to do a ping to router 1's loopback and I source it from my own loopback, we see that the ping is successful. If I ping router 3's loopback and I source it from my own loopback, we see that the ping is successful. So router 2 seems fine. If I come over to router 1, if I do a ping to router 2's loopback, we already know that this is going to be successful, but let's just verify. So that is successful. If we were to ping router 3's loopback and source it from our own, we see that the pings are failing. So right now, router 1 cannot ping router 3's loopback when he sources it from his own loopback. Okay, let's come over to router 3. So if we ping router 2's loopback and we source it from our own, this ping should be successful, which it is. But if we try to ping router 1's loopback, sourcing it from our own, we see that the ping is failing. And here's why the ping is failing. So we got to take into account how BGP deals with loop prevention inside of an autonomous system. And basically how it works is this. If you learn a route from an iBGP peer, you cannot advertise it to another iBGP peer. So what's happening is router 1 is advertising this loopback into BGP over to router 2. But since router 1 and 2 are iBGP peers, 2 then cannot turn around and advertise it to 3 because 3 is also an iBGP peer. Just like in the reverse direction, 3 is taking this loopback and he's advertising it to 2. But since 2 or 3 are iBGP peers, 2 cannot turn around and then advertise it to 1 who is also an iBGP peer. So that's why if you come and you look into the BGP table on router 1, if you do a show IP BGP, you will notice that router 1 does not know about router 3's loopback because 2 is not advertising it to him. We can verify this is if we come over to router 2, do a show IP BGP neighbors, we put router 1's address and we do advertise routes. Notice that the only loopback that's being advertised to router 1 is router 2's loopback. So 2 is not advertising 3's. Just like if we do the same thing for router 3 and we do advertise routes, 2 is only advertising his own loopback. He's not advertising 1's loopback. And that's because of the loop prevention mechanism. So we got two solutions for this. Number one will be to run iBGP everywhere. So instead of just running iBGP between 1 and 2 and 2 and 3, you will also run iBGP between 1 and 3, and you will have a full mesh. Now, you don't want to do this because as the number of routers increase in your network, so does the amount of peerings that you're going to have to configure. So it becomes an administrative overhead having to configure all of those peerings. Not to mention you're going to have to deal with all of those BGP updates and all of those TCP sessions that's going to have to be built. So the way you can determine how many peerings you're going to have to configure is this formula, and the formula says this. You have n times n minus 1 divided by 2, where n is equal to the number of routers that you have in your network. So I'm going to get my calculator out just so you guys can see this. All right. So right now we only have 3 routers in the network. So if we say 3 times 2, which is 6, and divide that by 2, right now we only have 3 peerings. So we would have 3 peerings if we had a full mesh. We would have the peering the routers 1 and 2, the peering between 2 and 3, and the peering between 1 and 3. So that's quite manageable because we only have 3 routers. But it gets kind of crazy when you start getting into a large number of routers because your network is big. What if we had 100 routers? Well, 100 times 99 is going to be 9,900. If you divide that by 2, that's nearly 5,000 BGP sessions you're going to have to configure if you were to do a full mesh of iBGP between 100 routers. What if you had 500 routers? If you multiply that by 499, you get 249,500. If you divide that by 2, now you have to configure almost 125,000 BGP sessions if you were to do a full mesh. So if you're trying to get around this loop prevention problem, a full mesh of iBGP peers wouldn't be the solution that you want to do because it's not scalable. Instead, what you're going to want to do is configure route reflectors. And here's how route reflectors work. We're going to configure router 2 to be a route reflector. 1 and 3 are going to be the route reflector clients. And as an update comes in from one of the clients, like router 1 here, 2 is then going to reflect that down to 3. So now 3 is going to be able to learn about router 1's loopback. Just like in the reverse direction, 3 is going to advertise his loopback up to 2. 2 is going to reflect this down to 1. Now 1 is going to be able to learn about router 3's loopback. So what we're going to do is we're going to go over the router 2. We're going to configure router 2 to be a route reflector. 1 and 3 are going to be the clients. Now you don't have to do any configuration on the clients. You only do this on the route reflector. So I'm going to come to router 2, and the command is simple. We're going to go to router BGP 123. We're going to say neighbor 21.21.21.1. That's the IP address of router 1. And the command is route reflector client. Now the neighbor is going to go down due to the route reflector client config change, and then it comes back up. We're going to do the same thing for router 3. Route reflector client. Okay, the peer goes down and it comes back up. So just to verify the peers are up, do a show IP BGP summary. So the peers are up and we are receiving their loopbacks. So if I do a show IP BGP, okay, we see that we're receiving router 1's loopback and 3's loopback. Now if I scroll back up, previously when we looked at what 2 was advertising to 3, he was only advertising his own loopback. So he was only advertising his own loopback to 3 and 1. But now that we have router 2 configured as a route reflector, that should change things. So now we can see that not only is 2 advertising his own loopback, he's also advertising 1's loopback and 3's loopback. Now it is being advertised back to 1, router 1's loopback, but 1 is just going to reject this, and I'll show you in a second why. And then if I do it again for router 3, we can see that 3 is now being advertised 1's loopback, 2's loopback, and his own loopback. So if I then come over to router 1 and I do a show IP BGP, now I'm receiving router 3's loopback in. if I do a show IP BGP for router 3's loopback, there should be in here where it says the originator ID. So let me just show it to you right here. So right here, oops, let me bring this back up. So if I look at router 1, if you look right here, it'll tell you who the originating router ID is. So whoever has this router ID, which happens to be router 3, he's the one who originated the prefix. Router 2 is just reflecting it. So if I was to come over to router 1, for example, or router 3, and I do a show IP BGP for 1.1.1.1, you can see where it says that router 1 is the originator of the prefix. Okay, it says it right here. So what's going to happen is, even though router 2 is reflecting this back down to router 1, which is its own loopback, 1 is going to see that he's the originator of it, and he's going to reject it. So for example, if I come over to router 1, I'm going to do a debug IP BGP updates. I'm going to do a clear IP BGP start inbound. And so you can see right here, it denied the update. So it received an update inbound from router 2. It was about his own loopback, but it was denied due to the originator is us. So even though 2 is reflecting it back down to 1, 1 is simply going to deny it because he's the one who originated it. But route reflectors, it helps us get rid of this loop prevention problem with iBGP, where if you learn a route from an iBGP peer, you can't advertise it to another peer. So previously we saw routers 1 and 3 could not communicate via their own loopbacks. Now that routers 1 and 3 are receiving the loopbacks via BGP, they should be able to ping each other, which they can. So router 1 can ping 3. Let's just come over to 3 and verify that he can ping 1. And we can see that they can ping each other. Now the good thing about this as well, or the thing to know, is that the route reflector, router 2 in this example, he doesn't have to be in the data plane. So what I mean is, just because router 1 is advertising his loop back up to router 2, and 2 is then reflecting it down to 3, it doesn't mean that if 3 is trying to get the router 1's loop back, that the traffic has to go this way. Okay, because what's happening is, when router 1 sends the update to 2, he's making this the next hop, 21.21.21.1, the IP address of this interface. When 2 sends it down to 3, he doesn't change the next hop. He's maintaining the next hop. So if I were to come over to router 3 and I do a show IP BGP, what you're going to notice is that the next hop for router 1's loopback is router 1. He's going to be the next hop. So it's not router 2, even though 2 is the reflector, it's going to be router 1. And then router 3 is going to say, well, how do I get to 21.21.21.1? He says that I have equal paths. I can get there via router 2, and I can get there via router 3. So he's showing that he has equal paths. So if I do a trace route to 1.1.1.1 and I source it from my own loopback, I can see right now he's kind of load sharing. But what I can do, if I want to kind of modify this, I can come onto the interface going over to router 2, which if I do is do show IP interface brief. That's interface FA1/0. I'm just going to make the delay higher. Right, so now the metric through router 2 should be worse. So now I can see that I'm going through router 1. So if I do my trace route again, notice I'm going directly to router 1. So even though the update came from router 2, in order to get to router 1, I'm going this way. I don't have to go this way through the route reflector. So just because the route reflector is reflecting the routes down, it doesn't mean he has to be in the data plane. But this is why we would have BGP route reflectors. We don't want to have a full mesh of iBGP peers to get around this loop prevention mechanism that BGP has within an autonomous system. Another solution you have is BGP confederations, which I'm going to save for another tutorial, but we can implement route reflections as a solution as well.